Hello, everyone. Thank you for joining me today. I know as engineers, time is precious. Well, for everyone, time is precious, but I know engineers are especially busy. So anytime you can spend your attention with us, highly, much appreciated. We take that pretty seriously. So we'll go ahead and get started. We're quite timely. It's 10 a.m. here in Colorado. So wherever you are at, or whenever you are at, if you're in the future, again, thanks for joining. We're going to talk about meeting code for pipeline pressure surges, looking at ASME B31.4. It's a specific piece of code on pressure piping that is relevant to, well, engineers who deal with fluids. So hopefully you learned something today. That's the goal. My name is Walt. I am an engineer here at AFT, do a little bit of everything, sales support and all that. So today I am your presenter. I would like to encourage you, if you have questions, please put those questions in the little questions chat area that you have, and I will try to address those. I might get to them at the end, or I might get to them during the webinar. It really just depends on the question, the flow of things, but I encourage you to do that. So, all right, let's get started. First, we will talk about what does ASME B31.4 say about pressure surges? Probably a good place to begin. We will look at how we can analyze those pressures in Impulse, because one of the things we'll see is that they tell you to look at surge, but not necessarily how to. So we will use our software tool that we produce, AFT Impulse, to do that. And then not just use the software to figure out what your surge pressures are, but possible mitigation methods. So 3 main points. It's not the longest webinar in the world, but there's still a lot of good content. So I'll try to keep things moving, but slowly enough so hopefully you can actually understand what's happening, because I know transient analysis can be a little tricky, okay? But before we get too far, I always like to talk about safety, and this is something that was super relevant to me, so I'd like to pass on the knowledge. It's more of a story, but it's been surprisingly nice weather here in Colorado for this time of year. So yesterday it was really nice out, sunny. So after work, I went for a little run through one of the local parks here, trail running. And I kind of just kept going because I liked it and I was feeling really good. But I think I might have pushed it because I got some cramps in my calves, and today I'm suffering and I got a limp in me. So anyway, moral of the story is if you are going to be doing something, think long term and build up your strength and health. There's no need to rush it all in one sitting like I did. Very short term thinking, not good. I mean, I have the rest of my life to run, and risking an injury is not worth it. So I encourage you all, don't be like that. Take it slow. Okay, so now let's get into the meat of the webinar. The first question, what does this code actually say? Well, I say intimidating things. It's kind of like this looming danger over these surge pressures, right? The reference I have is ASME B31.4 from 2012. So they have updated things, but it's all pretty much the same. It's all very similar. This is just the copy we have in reference, but again, the idea is going to be the same. In paragraph 403.3.4, they say, surge calculations should be made and adequate controls and protective equipment shall be provided so that the pressure rise due to surges and other variations from normal operations shall not exceed the internal design pressure at any point in the piping system and equipment by more than 10%. So some key things to highlight are the words like should versus shall. Minor differences you might think, but one is saying it's suggested and the other one is saying you kind of have to do it. So they suggest doing calculations to make sure your equipment is adequate so that for sure your pressure surges don't go above 10% of the design pressure of your piping and components. Well, it's kind of hard to give a suggestion and say you can't meet these, you cannot meet too high of a pressure and say you should do you have to do calculations, but unfortunately they don't really tell you how, and that's where our software comes in. So what I want to do is pull up the code, the big book. B31 is for pressure piping, and this chapter specifically, B31.4, is on pipeline transportation for liquids and slurries, thus the name of the webinar. So if we scroll down to, let's just look at some table of contents, we will be looking first in our loads area, because so all of this, and actually my background is chemical engineering, so I'm not as familiar with mechanical engineering codes, but it relates because the codes are mostly about the materials, making sure they can handle whatever process you have. But what is going on in the middle of those materials, that's fluids moving through those pipes, right? And having these pressures, and that's what's going to, it will be from the fluid that you have those surge pressures. So you got to make sure your pipes can handle it. So the code is from the perspective of the material, of the actual, pipe, make sure your loads are okay, you can handle the stresses. And where we come in is from the fluid side, which is just inside of those pipes. So it still all relates. But anyway, we're going to be looking at loads. I bring it up because loads is not something you usually think about with fluids. So anyway, we scroll down to page about 30 in the PDF or 11 in the actual code. Okay, talks about loads, cool. And then we see something here about transient loads. That's a thing, meaning stuff just sits there. That's what we would call steady state, or if it's a fluid, it's moving and nothing is changing with time. But then something happens and that causes a reaction. So surge is one of those reactions. Neat, that's where we come in. And then over here is 40122, specifically talking about pressures, and down here, pressure rise above maximum steady state operating pressure due to surges and other variations is allowed in accordance with this paragraph. So they do a lot of self-referencing in these codes. So it's really this area is going to tell us what we can and can't do. So what I will do, as the great engineer I am, just kidding, is Control C, Control F, and Control V, so I can find where this paragraph is at. There we go. Okay, criteria for transient overpressure. That's a fancy way of saying pressure surges. And in here, they give a little snippet about what is surge, okay? Transient overpressure includes pressure rise due to surge. Surge pressures in a liquid pipeline are produced by a change in the velocity of the moving fluid. So you have steady state operation, then you change the velocity of the fluid somehow, that causes a reaction in the fluid. And really it comes down to converting kinetic energy into potential energy in the form of pressure. So that can happen when you shut down a pump, it can happen when you close a valve, or you block the moving fluid, but something changes, right? And then here's where I got the snippet in my presentation. Surge calculation should be made in adequate controls and protective equipment, blah, 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 blah. And then it skips, let's pass the table of these stress informations, and down here, okay, you can't exceed your design pressure by more than 10%. So this webinar is really at the center of it. It's a very simple concept of just make sure that you know your design pressures. Don't go 10% above that in whatever worst case scenario you might be analyzing. The tricky part comes in, again, the execution of how do you figure that out. So maybe it would be good to go over some definitions. So you have your operating pressure. That's typically, that's the pressure you're operating your system at steady state. So you have a certain pressure, and then some margin above that is going to be your design pressure, which is kind of like the max pressure for the pipes or something like it's designed to handle, okay? And so the code allows you to go 10% above that, the design pressure. So again, operating is typical steady state operation, design pressure is some margin above that, and then the surge allowance is, again, some margin being 10% above the design pressure. So it's not unlike Gordon Ramsay yelling at you to do surge calcs, and you're sitting there wondering, I have no idea how to do this. You might sit in frustration. Well, that's why you're here today, to learn how to do this. That's where AFT comes in. So we're going to go through a little example. Well, maybe not little, but an example to kind of walk through how the basics of setting something up like this in Impulse, and then also how you can use it to specifically meet that code that we brought up. This is not an in-depth tutorial on how to use Impulse. So I am going to assume you have some sort of background, at least with our interface, whether that be from AFT Fathom, Aero, Impulse Extreme, that you kind of understand the concepts of fluid modeling in this way. So we have this pipeline, a system that is really just a single pass pipeline. You know, it's not part of any process plant. We're just going to assume it has some upstream source passing oil through this pipe. This is an oil pipeline, so obviously you don't just have to work with oil and gas and its derivatives. This could apply to water as well, but I'm just going to use oil for the heck of it. And we're delivering to some other downstream source. So in the middle, we have a very long pipeline, and with pipelines, as the code suggests, you typically have to worry about surge. Simplified calculations, or just assuming some, oh, my system will be good enough, is not good enough, because there's lots of things that can happen that are unexpected that simulation software can help predict. One of those being, because it's such a long pipeline, 5 miles, 3 miles, or longer, 100 miles, there's a lot of pressure loss from friction. When you close a valve and that stops the flow, not only do you have a pressure rise from suddenly stopping the fluid from changing that velocity quickly, you also have additional pressure rise from recovering all of that pressure loss that was occurring because it's such a long pipeline, and it's like a pressure on top of a pressure called line pack. So anyway, simulation software helps predict that. And we will look in AFT Impulse today because that's the software we produce. Okay, so let's move over. And here's our example. This is the interface of AFT Impulse. So again, I'm moving oil from one pressure source to another. And in this case, I'm going from 570 pounds to delivering at 470. Okay, and in the middle, in order to do that, we have a couple pumps. We have the main pump station, then a booster pump station a little further down, just to be able to maintain the higher pressure to keep things moving. Again, this is just our example. So whenever you do transient analysis, it's good to run a steady state solution first to make sure before you kick in any transient event, things actually make sense, you know, as from a steady state perspective. So we have these pipes, they're 12-inch pipes, not very big. And then we have these pumps, which each of them have a pump curve associated with them. The valves all have information. So here I've got check valves, which will be more relevant in the transient scenario when they will close. And then here we have this emergency shutdown valve. So at steady state, it's just an open valve, and it's just a ball valve, and it does not have a lot of loss with it. So it has a very high CV of 10,000. So we're just going to assume it's completely open, so at 100% open, and at steady state, right, that's not changing. That just means it's pretty much a lossless valve, right? And it's a ball valve, that makes sense. But we will use this to do our emergency shutdown, and that will have certain implications, but at steady state, no problem. So I can run the simulation, making sure everything's defined. And what I will do is I will look at a pressure profile. And what I do is highlight pipes, profile for pressure static. And what I'm looking at, I'll change this to pounds gauge, is I'm just looking at steady state. How is my pressure changing with length? So here, right, I've got my pumps, neat, pumping up the pressure of the fluid, and delivering from having been supplied from one pressure, delivering to another. And I would say my operating pressure is around 600 pounds. So at max, it's about 625-ish. So my operating pressure is here. Hopefully my pipes have a design pressure higher than that, right? So if my operating pressure is around 600, we probably want the, well, I guess in this example, I'm not going to tell you what you want. You guys are far more experienced in this stuff than I am. I'm just presenting from the software perspective, but something like 700 pounds is at least above the operating pressure. So let's say this should be our design pressure, 700. Okay, cool. So that's our reference, right? That matters because if we want to look at the transient side, we want to make sure to not be 10% above that. Okay, so we'll call 700 pounds our design pressure. Neato. Now, an impulse, just like in any other software you can create a scenario, a new scenario, which is really just a copy of your model where you can test different cases without interfering with the original. It allows you to just test multiple things within a single model file. So I have a scenario here called Transient. I'm going to open it up. It's going to look very similar. The difference is I've switched the solver to be a transient solver now. And so any transient information I put in is denoted with a T. So we'll walk through just a little bit of that. Steady state's fairly simple. Transient gets a little more tricky because you're just adding that third dimension of time can really, well, it makes things that much exponentially more complex. Luckily with software though, it's a lot easier to navigate and you actually have an interface to work through. So first we have to say, what is our transient that we are going to cause through the system? Well, in my whatever project you're working on, you might have different stuff, but for me, I want to look at what happens when we need to have an emergency shutdown. So something happens maybe downstream and we need to close off this pipeline. So we need to close this valve, which is a transient event. So if I go into my valve, I can go into this transient area and specify specifically how to close my valve. So all this is saying is that in 5 seconds, I'm going to go from fully open to 0, meaning closed. CV of 0 means no flow. So I'm going full open to closed in 5 seconds, and then we will see what happens. And there's a lot more information you can see in the window. So for instance, you can see that that's how my CV is behaving. My open percent has a little bit of a different behavior to it because valves have characteristics with them, which we saw in this graph. We have other webinars about valve characteristics specifically. So again, can't really, or don't want to spend too much time on those deeper topics. This is going to be a broad overview, but the idea is we're closing the valve. So I think you can get behind that. When we close this valve, I already know it's a good idea probably to turn off your pumps because otherwise you're deadheading and you're going to cause even higher pressure rises, which is certainly not good when we're looking at surge. So these pumps, what I'm telling it to do in a similar way, it has a transient tab. I'm going to tell them to trip. They're going to shut off, and that requires some inertia information because things will still be rotating even if the power cuts out. And I will do that only if my valve percent is less than 50, meaning it's closing. If my valve is closing and it gets to 50% closed, that's enough for me to say I need to turn off my pumps because that means something's happening. Otherwise, this valve wouldn't be, nothing, the valve wouldn't close otherwise. So I have all 4 pumps triggered to shut off when this valve shuts off. That's at least one way to, well, it's a good idea to prevent high surge pressures just on its own. But 5 seconds for the valve closure, maybe that's not long enough. Maybe that's too quick. Maybe it's just fine. I don't know. That's what the software will help us with. So if I set up my transient information, I will go in here just to quickly note this, that I'm going to run the simulation for 2 minutes. That doesn't mean it takes 2 minutes to run in the software. It means if I was standing outside and looking at this pipeline, it would be like looking at it for 2 minutes. So seeing the pressure waves move back and forth for 2 minutes. That's important because you need a long enough time frame to capture waves moving back and forth. There's a concept called communication time in transient analysis. So as we close this valve, how long does it take for that information to get upstream? And the way you know that is you know the speed of sound. Well, the speed the wave will travel at through the pipeline, which is a function of the fluid, its density, the pipe, the material, and all that. But it's effectively, how quickly does a sound wave move upwards? So in this case, the communication time, which is there and back, is 30 seconds-ish. I think it's more around 25 seconds or so. But anyway, we need a long enough simulation time to capture that moving through. So if it takes at least 30 seconds to move back and forth, then I don't want too short of a simulation time, right? Then I'm not capturing everything. So under 20 seconds in this case seems good. I'm going to run it, Control R, and you see, so it doesn't take 2 minutes to run. Of course, I've set this model up in a very nice way so it runs quickly. Depending on how you section things, it might take longer. Again, we have resources and other webinars and blogs and stuff like that to help with runtime. Okay, neato. So we ran the transient. What happened was this valve was closing, then those pumps shut off, and we're going to see the response. We're going to see how the pressure changed. So why don't we look, let's first look at output. It's a chance for me to show how you can show output on the workspace also. It's really cool. So if you set up a layer in Impulse, there's a parameter called max transient pressure, and you can actually display that on the workspace. And I've gone through and already created that, so I'm just going to show that layer. So what we see here is it will report P max transient. That's what that means. It's just maximum transient pressure. So we have all these areas, on all of these pipes, we are seeing what the maximum transient pressure is. And it's just it's a nice quick glance, something if you wanted to report on or kind of just do spot checks and all that without having to look at output with there's just a lot of data, right, to look at. So here immediately we already see 834 and the units down here in the legend is pounds per square inch. So that's pretty high. That's quite a bit higher than my design pressure of 700, right? So, okay, that already is kind of flagging me. Interesting. Let's go ahead and look at the pressure right at the valve, because in proximity to the event to the component that is causing the surge tends to be where the extremes are at. So let's just look at the pressure into this valve. If I right click it, I guess we can start with CV to see how it's closed. So it closed over 5 seconds. I'm going to change to show the pressure into it. Okay, so this graph looks noisy. Don't worry, there's not too much going on. It's just what is the pressure right at the entrance of the valve? What does that look like? Well, for the first little while, it's steady, because as the valve is closing, it turns out it's actually not controlling flow much, but it's around that, I guess, the delivery pressure up to the other downstream side, maybe about 480 pounds or so. And then it skyrockets from the valve being closed. So remember, kinetic energy converting to potential. We're seeing this pressure rise, and then that will cause flow to stop. And then there's a bunch going on with the waterhammer cycle, where waves are reflecting off each other, or waves are reflecting off components. We have the check valve, which ends up closing, so it kind of locks in a pressure wave here. When you do transient analysis, there's so much you could look at, and it's a good skill to be able to kind of ignore too many things at once and look at one specific thing. So I'm just going to look at the pressure in the valve and see that, okay, so it oscillates, but it stays pretty high. It hovers around 800 or so, or a little less than that. Okay, so that probably means the pressure in the other areas are going to be similar, maybe a little bit less. But my max pressure was 834 in the pipeline here. That's probably no good. So let's do some quick math. If 700 is my design pressure, what's 10% above that? That's going to be 770, yes? Cool. You can tell the software to warn you anytime that pressure is reached and you're violating your own code. Sad face. So the way you do that is through a design alert. In Tools, Design Alerts, add, I'm going to say max P is the name of it. I'm going to apply it. I'm just going to apply it to my valve for the sake of ease to say if the pressure into the valve is any higher than that, then I will assume, elsewhere it could also be a problem. You could also apply that same logic to pipes and just choose all of your pipes. And in fact, that's a really good choice. It's just I'm going to have 12 design alerts then show up. So I'll just stick with valves for now. I don't want to look at CV. I want to look at pressure into the valve and alert me when it's greater than or equal to 770 pounds gauge. Now I choose to apply it to my emergency valve right there. And so when I run my simulation, it will evaluate the pressures at that valve and see, is there any time it's violated? Oh, and lo and behold, it is. And this is how it shows up. It shows up in a design alerts tab down here or up there, and down here, kind of like a warning. It lets you know that there's a problem, or at least according to what you said would be a problem. So we don't necessarily look, we don't look at the code directly because every pipe and system is different. But this is a way you can still put in that logical check in the software. It's just you need to know what your max, you need to know your design pressure and whatever the 10% on top of that is. And then it will warn you. And here, if I look at, let's see, it's just that again, no, not in there. Well, if I have in my valve summary, if I look at any pressure that's into it, it would highlight yellow from being above 770. The problem is this is a steady state check, not the transient. So it tells me my pressure in right now is only about 500, or I guess, 480 or so pounds gauge. That's the steady state. The design alert tracks through the whole transient. So it looks at any time the pressure might go above 770, which is why it flags. So it tells you the first time it happens is at 11 seconds. And if I go back to my graph, or sorry, let me create another graph. I'm going to right click. I'll do it from the graph interface to show you something different. Okay, choose my transient junction valve, pressure static inlet, PSIG, and I have a nifty little button here, the DA checkbox. I can check that. And what this does was it will plot that design alert I had at 770 against the actual pressure I'm seeing in the system. So I can see it is most certainly violated, right? If my design alert's at 770 and my pressures are anything above that, well, I guess that's what we're seeing here. Let's see. Okay, so that's an example of how you can use the software for looking at surge pressures and checking, are you meeting code or not? That's awesome. Let's say you're not meeting code, like in this case. That's about, 10% of the story. That's cool. The bigger deal is, how do you make sure that doesn't, or how do you make sure you can get away from that? How can you mitigate this problem? Another beautiful feature of this software is that you can test those things. It's like a what if situation, right? What if I close my valve differently? Hey, that might mitigate the problem. And that's actually what I have done here. So I just swapped to another model, which was pre-made, but I've created a couple of different scenarios. So again, I assume you have some familiarity with our software. Just created a couple of scenarios that are good for testing. So the bad valve closure that I labeled here is just closing it in 5 seconds. Maybe that's too fast, okay? And again, I have my design alert set up already in this model, so I can see that was violated. Cool, we already went through that. Let's look at what might be a good, actually, no, sorry, hold on. Let's look at the bad valve closure again. There is something I want to show you, which is the valve profile over time. Okay, so what we have here, I pulled up a graph. We're looking at how the valve is behaving through time, specifically in the first 6 seconds. So a very zoomed in picture of this whole simulation, just the first 6 seconds. This valve, if we look at the red line here, the CV is going from very high to very low in 5 seconds, okay? It's closing in 5 seconds. We look at the flow rate or the velocity, either one, into the valve. Do you see that it doesn't change at all? Not at all, but it hardly changes until about 4.5 seconds. What this means is this valve is so big and lossless that as we're closing it, it actually isn't even controlling flow. It's not causing any restriction until it's really late. We would call the effective closure time here about 1/2 second. So even though you're closing your valve in 5 seconds, really to the system, it's like closing it in 1/2 second. The effective closure time is very small here because it's such a big valve to begin with, or such a lossless valve. That matters when we go into how might we want to then have a better valve closure. Well, you might imagine then maybe we get down to a CV of 2000 very, very quickly because it doesn't do anything to the system. Okay, so if we get down to 2000 very quickly, maybe we can get, after that, get down to, I don't know, maybe 1000, a little more slowly. And then for the last part of the valve, close it even slower. So this could be a staged approach to your valve closure. So obviously that would require some sort of unique actuation, but in theory, it's possible. So that's what we're going to test is what if we do a different type of valve closure, we stage it a little bit and we extend it past 5 seconds. So that's what this good valve closure is looking at. Same idea, right? We're closing the valve. The difference is I'm not just shutting it off in 5 seconds directly. I am going very quickly, which is probably unrealistically quickly, but you could do it quickly. Shut your valve for the first part of the valve fast because the rest of the system isn't even noticing the valve is closing. And then start to slow it down a little bit. And then really at the very end, we're going to take 15 seconds to go from very closed to actually closed because it's that last portion that matters a bunch. I think it's known as like the 80-20 rule, kind of along Pareto's principle, but the last 20% of a valve closure can cause 80% of the problems. That's a very simplified rule of thumb. But that idea is played out here. So it's the last portion of my valve closure that could cause the most damage. So anyway, I'm going to smooth that part out and not worry so much on the front end. Same idea, pumps are going to close or shut off, and these check valves will close as soon as the valve closes and all that. And again, because I'm running this valve closure will take 30 seconds, and communication time is also another 30 seconds on top of that. I want to make sure to have adequate time to run my simulation, so I'm doing it for 2 minutes, which should be good. Okay, I run this. Okie dokie. I have, by the way, the same design alerts applied. I just didn't show you that. It's the exact same idea. I have the max transient overpressure here, 770, okay, into my valve. And you can see, oh, I have absolutely no design alerts. That means probably met code. That's a good idea, or that's a good outcome. So if I look at my output, again, I can just display it on the workspace, nice and easy, is, oh, my maximum everywhere seems to be 700 or less. So all of a sudden, I'm now meeting that code, and I can present this to a client or to whoever you're working with to say, hey, this is proof is a hard word, but this is suggesting that closing a valve in this manner would help prevent surge and help us meet code. And I like to emphasize all of our software, or this Impulse is nuclear verified. So we go through the rigorous testing to make sure our calculations are legitimate. You can use this to say, hey, meaning you can use this to say, this is how I'm deciding to meet code, right? The calculations are legitimate as long as you know what your design pressure is and the max transient overpressure. the software is a good, a CYA move, if you might call it that. Okay, and now if we look at how the pressure at the valve in this scenario looks, we can pull that up. By the way, with all those graphs I was making, you can save them, which I have in this model, a nice little feature. In any case, what I'm looking at is the pressure, again, into my emergency valve. And I am plotting my design alert alongside it so I can see when it's violated or if. And in this case, as I'm closing my valve, the way I've done it has prevented major surge moving through the system. There's still some, because remember, you have the recovering of the frictional loss, you still have a change in kinetic energy, so there's still a pressure rise, and that kind of gets trapped in that check valve, all of that. But much better than just closing it over 5 seconds. A lot of you might say, you know, obviously you close the valve slower, that's going to be a better idea. That's going to be, you're going to have a better outcome. And I would say yes, but remember, you have to still worry about the idea of the controlling CV and the fact that the first part of the valve closure pretty much does nothing. So that's why I did the stage approach, to make sure it's not just that I extended it 30 seconds, it's also that I did it in a different way. So anyway, you might need to rewatch this a couple times to capture it. I know it's a lot of information, very dense. Okay, well, something nice about the software too is I can plot this graph over the other scenarios graph and get a direct comparison, and again, present this to a client or something and say, this is why you need to close this valve this way. Because if you don't, the red here, and I zoomed into 60 seconds, so that's why the graph might look different than before, but it's the same graph, it's just zoomed in. And I could look at the whole 120, but it just looks a little more noisy, so I zoomed into 60 to get a little finer resolution here. In any case, the red graph is showing the bad valve closure, where I'm just closing it over 5 seconds, not concerned with how I might be closing it. And we have, well, pretty high pressures, and we're going to violate our design alert of 770. With multi-scenario graphs, there's no design alert option like there is in the single scenario one, because we just don't know what, if the design alert might have changed between scenarios. It's kind of the nature of scenarios is that things can change. So anyway, you kind of have to use your imagination when you're doing the multi-scenario side. But you can have these crosshairs here, which tell you, again, in the purple on the left-hand side, you can see where 770 is and that you're violating it. Okay, and then with the good valve closure, hey, you're not. Okay, and again, this was assuming the pumps shut off, which was, I guess you could run a scenario, what if we don't shut the pumps off? You're going to get even higher pressures probably, and certainly not meeting code. So just kind of another thing you could do with the software. There's endless things you can do. Neat. Okay, one last mitigation effort I would like to test out, because it's common with pipelines, is a surge vessel. So for those of you who don't know, a surge vessel is a big tank charged with gas, usually with a bladder. I mean, I guess there's a lot of configurations. But the idea is a pressure wave can move through and it gets absorbed by the surge vessel, because a gas is compressible and it'll compress the gas and kind of smooth out the otherwise problematic pressure you're going to have. And it can also deliver pressure if there happens to be low pressure to help prevent transient cavitation, topic for another time. The idea is a surge vessel, what's that word? I can't think of the word I'm thinking. Dampening, I guess it dampens everything out, okay? So what I've done is I've defined a surge vessel. We have resources on what these things mean. We also work with someone who designs these and actually, manufactures these physically and can install them. So if you do have an interest in installing something like this, give us a shout. We can help get you in contact. So what this will do is, as my valve closes, I'm still going to assume my bad valve closure of 5 seconds. We're going to see how this accumulator, in our software we call it a gas accumulator, but it's just a surge vessel and there's so many names for it, how that will help or hurt the situation. I guess you can, because I add the layer on, you can see it already. It helped the situation because my max pressure is only 600 here. Anyway, let's go ahead and shut that off. Okay, now let's run it and pretend we didn't already know that. Go to output just to see no design alerts again. So that leaves us happy. Neat. And if I go back, we can see that output again. By having the surge vessel here to absorb any of the high pressure waves, our maximum pressures through the system are not nearly as high. Another way we could mitigate the pressure. Now this one downstream of the valve is still pretty high, 750. That's because we closed the valve, which would have caused a low pressure wave to move through, but it's a wave cycle, so what comes back is a higher pressure wave. So we might need something on the downstream side to get that down a little bit more, but technically still meeting code. We can look at again, the pressure into the valve, and we're going to see some interesting behavior. It doesn't look like it's dampened out. What is happening is the pressure wave's moving and it hits this surge vessel, and it's kind of coming back and forth between the vessel and the valve, but it's keeping the pressure in that area, because if we look instead upstream of the vessel itself, if we look right at this point, we'll see a very smooth pressure rise, almost like nothing happened. So transient pipe graph for pressure and outlet of that pipe. We will see, thanks to the vessel, the pressure on for the rest of the system is no problem. It's smooth sailing. You're gonna have the check valves closed, pumps are off, everything's protected, and you're way below the minimum. You're barely even above 600. So remember, our case design pressure is 700. Okay, and again, we could look at the multi-scenario graph with that case going on, but I think you get the idea. There's so many other mitigation methods we could go through. Relief valves, if you're, well, I guess that's more for process, like in a processing plant or so, something like that, you discharge to a header or something like that. But there's other mitigation methods and prevention tools, which is what the code talks about, right? Make sure you have components to help with surge. That could be the surge vessel, that could be better valve operation, that could be an air valve we have here, that could be a relief valve, that could be another type of control valve and open up to another line. Many ways you can test helping the surge that happens. And that is up to you to figure out what is the most viable option, right? Anytime there's an upset event in your system, you need to figure out, well, what's the best way to mitigate this, right? Software is way more efficient. It's way more efficient to use that than to do anything by hand, and it's much safer than just guessing. Even though I know guessing, it's kind of fun, it's like a gamble, but people's lives are at stake, very dangerous. Nuclear verified software helps with it. So here's a screenshot of just the valve closures, excluding the surge vessel, just for simplicity's sake. But if you close the valve in a better way, you meet ASME B31.4's requirement for transient overpressure. Okay, so that's really the end of what I have to present on. And like I said, it's a fairly simple concept, not going above 10% of your design pressure, and that's how you might do it in Impulse. You might be somebody who's watching and saying, dude, I have no idea how to even open Impulse, let alone use it. Luckily for you, we have resources on that. So an example here is we have a webinar, how to use AFT Impulse. If you Google it, which I did, how to use AFT Impulse, a few things come up. We got our sponsored ads. You don't need that. What you need is down here, this webinar, how to use AFT Impulse on YouTube. We also have other resources like this. This is what we call training. It's a series of 5 videos. Point is, there's ways to learn it. I can't teach you everything in a single webinar. And another thing you can do to learn the software, assuming you have the software, is in our online help guide, which let me go back to the software. If you go to help, use open help. It'll open in your browser like this, and you can, well, for examples, go down to examples here, walk through examples, and it gives you pre-made problem statements that you can just kind of practice using the software. And again, getting through the idea of how do you set up your simulation time? How do you actually define the transient and all of that? And then you do the analysis. It'll walk you through making graphs and all that. So I like walkthrough examples because hands-on is always, I mean, it's so much better than just watching this presentation. It's a good, decent presentation, I hope. Maybe you learn something, but getting your hands dirty is where the magic happens. Okay, so it looks like I didn't have any questions, so maybe that's a good thing, maybe not, I don't know. Let's see. A surge valve, I have a question here. Do you recommend a surge valve, not a PSV, pressure safety valve, to mitigate transients? Lots of operators use it. Thank you, Ray. To be frank, I'm not sure. I'm gonna have to do some research, talk to some colleagues about what specifically happens with a surge valve beyond just a relief valve or a safety valve. So I love the question. I like that you're engaged. I'm sorry I don't have the answer for you, but I'll go ahead and find out. I guess it would also, it's hard for me to really recommend anything over something else because, as you know, engineers, we always like to say this, it depends. A lot of times there's not really a straightforward answer for any. There's a million types of systems out there. Hardly is there a single solution that catches everything. But I'll take a look into it and tell you what I think about it. That'll be after the webinar. So, okay, well, for the rest of you, hopefully you enjoy the 13 minutes I gave back to you. Oh, what do you recommend for any beginner using Impulse? Okay, got another question. Excellent. From Mustafa, what recommendation for any beginner? Do I have any recommendations for beginner Impulse? Yeah, that's to watch this stuff. I mean, the best thing you can do if you're a beginner is learn how to use the tool. And we have, I mean, dude, we have endless resources on learning Impulse, and not just Impulse, but waterhammer in general. Surge analysis, it's the same thing. Because understanding the theory will give you such a head start in actually doing the analysis in the software. Learning the software is great, knowing where to click buttons and add things and all that is awesome, but you need to understand what's going on. And the theory will really help with that. And we have plenty of that. If you just Google AFT, waterhammer webinars, we go through a lot of theory too, not just software stuff. Okay. Why is the steady state resulting pressure higher for the one over the other? Rick, I'm really sorry, I don't quite understand the question. If you wouldn't mind you can toss in another question and try to expand on it. I'll do a better job I'll try to do a better job of understanding it. Thank you for bearing with me. Okay, so Ian asked an interesting question. He's saying, building a model in Fathom, which is our steady state solver or steady state software, bringing that into Impulse and running in steady state. Why might the results be different? Oh. Let's go. I need to go into Impulse, I'm sorry. There we go, that's what I'm trying to do. One reason is that our solution control is a little different in Impulse than it is in Fathom. I hope at least that it's not terribly different where, I mean, you draw different conclusions, but we have different settings on the back end where what we consider a converged solution, it's a little tighter in Impulse at steady state than it is in Fathom. Another reason might be the fluid properties possibly a different, I don't know if it's might be a user specified fluid, in which case it should be the same. But if it's using a standard fluid, there might be reasons we have a slightly different value in impulse because we have to capture things like bulk modulus, for instance, when we're doing transient, that the source might be slightly different. Okay. Model priming is, okay, so Alicia asked a really good question. Do you have any resources to model priming a system, or getting something started, right? Dropping propellant into an initially evacuated line. Sadly, no, Alicia, for right now. One of the major assumptions of our software is that all of the pipes are pressurized, being liquid full. So we can look at things like air valves, but it is a very touchy subject where you have to understand that we still do the math assuming all the pipes are full of liquid, and it's kind of like a theoretical, well, this is how much air would be coming into the system, but we're not actually modeling it. It's not a two-phase solver. So when you are priming a system, we are not looking at the moving boundary of that liquid displacing the gas. That's what it comes down to. It is one of the limitations of impulses. It assumes it's going to be liquid full. However, I will say that maybe for those watching the recording, in the future, that is something we are trying to develop, is how do we capture that moving boundary of starting up a system. So when that comes out, Alicia, that's how you would do so. Okay, and we have another, or trying to clarify the question of the resulting pressure is higher for one of the other. The thing is, the steady state pressure should always be the same, but let's look at the graphs. Okay. Oh, that's not what I wanted to look at. Sorry. Oh, classic. I got to go into the right scenario first. Okay. So the way I'm seeing it though, Rick, is that they are the same. Let me zoom in further. Let's maybe even do 1 second. We can do time scale. So both valve closures start at pretty much, I mean, they are the same, right at about 480 pounds. And then it's not until the valves start to close and again, it starts to actually control the flow. And let me do 6. That's where things start to differ. And the reason for this increase and then a slight dip, I'd have to look in more. I don't know off the top of my head, but there's a lot of, it's always about the relationship between kinetic and potential energy here. So that's what's going on. So I think, anyway, for those who are not reading the question like I am, I apologize. The question is, if we have, all we're doing is changing how we're closing the valve, shouldn't it start at the same steady state point? And the answer is yes, it should. And that's what we see. Let me check my presentation to make sure that it's also there. Yes, okay. It just might look a little different because we might be zoomed out a little bit. But if you zoom in, these are the same for the first part. Okay, no need to belabor things. Again, well, now you got 5 minutes back in your day. Yay. So if you have any other questions, though, that's what this is for. You can email us, let us know you had a question on the webinar, and we'll find the right person to help answer it. So who's the person I have to follow up with? I got to follow up on what a surge valve is. Yes, with Ray. Okay, so I'll do that. But for anyone else with lingering questions, let us know. We're sitting here in Colorado in this office. We are real people, so don't be afraid to call us and email us. We'll help you out. All right, thank you all. Appreciate your time.